Okay. Hi, everyone. My name is Romain Michon, spelled absolutely perfectly before. I'm very, very happy to be here today. And I'd like to thank Mary Sheeran in particular, who actually asked me to come give this, this presentation at Lambda Day. So it's a really great community. I talked to many of you throughout the past 2 days. And so thank you. I'm very happy to be here. So just to start this presentation, I'm going to give you some information about who I am, because I don't really know you. You probably don't know me. So I'm in academia. I'm a research scientist at INRIA, which is the French National Institute for Digital Sciences and Technology. I did my PhD at Stanford in the United States at the Center for Computer Research in Music and Acoustics. So my background is more in electrical engineering and on the hardware side of things, even though I've been working on functional programming languages for a lot of time now, Faust in particular. So my research focus is mostly on embedded systems for real-time audio signal processing applications, and the Faust programming language that I'm just about to talk about in this presentation. And finally, I also make musical instruments as a hobby, and so this is, for example, one instrument that I've made. It's based on an iPad. It looks like a guitar, and it runs a functional programming language on it, and all the audio processing happens on the iPad on the guitar. So yeah. Anyway, this is the outline of this presentation. So first, I will show you what Faust is. Like, who heard about Faust here? I mean, like the programming language. Okay, that's actually quite a few people, so that's very nice. Sure, like everyone knows about Goethe's Faust, but like Faust as a programming language, maybe less so. So I will tell you about Faust. I will give you a demo of Faust. So we're going to write some code together, which will hopefully lead to a smartphone application that you guys will be able to install on your phone. We're going to try to play some music together at some point, we're going to try to make some sound together, at least. And finally, I will talk about the research that we do in our team at INRIA related to Faust, but also embedded real-time audio DSP, to show you some applications of research that we do with Faust and with this functional programming language. Okay. So first question is, what is Faust? So Faust is a domain-specific language for real-time audio digital signal processing. So here there are two important things to note. One is real-time. So we're only looking at real-time applications with Faust. We can do also not real-time if we want to, but real-time is the key here. And digital signal processing, I'm sure you all know about this, but especially for audio. And this is what we're looking at with Faust. So Faust was created by a person named Yann Orlaret. He's French. He was working at this institute, which actually is pushed by the Ministry of Culture in France. So it's completely outside of computer science. It's a little bit like IRCAM for some of you who know of it. And Faust has been developed since 2002, and initially at Graham, and now by a worldwide community of users and developers. So Faust is a compiled language. So you write something in Faust, you give it to a compiler, and then the compiler will generate code in lower-level programming languages, which for most of them are languages that can generate binary code, basically. Why? Because we're looking at real-time applications, and because we're looking at real-time applications, we have some constraints, so we need to talk to the machine directly. So initially, Faust would go from C and C++, to C and C++, and now Faust supports a lot of other languages like LLVM, WASM, and also hardware description languages for FPGAs. And there was a very nice presentation yesterday about FPGAs, so I'm going to talk about FPGAs later in this presentation. So the code generated by the Faust compiler can be automatically wrapped in a series of architectures. So when Faust was created, it was really designed for people who don't necessarily have a background in programming, but who are sound engineers, artists, musicians, and who don't really know how to code, but who know like basically how audio signal processing work. And so, so it was a way for them to basically make their own tools without having to write C or C++ or like lower level languages, you know, that are kind of out of reach to a lot of people. So, so the wrapper system of Faust basically allows you to export a Faust program to a platform and to create, for example, like standalone applications, audio plugins, smartphone applications, or things like that. You know, like, so this is what we're going to do during the demo after this quick introduction here. So Faust comes with a series of open source libraries written in Faust for signal processing, and that's one of the main strengths of Faust. We're very lucky because at some point, very famous Stanford professor named Julius Smith, who's one of the father of physical modeling of musical instruments. He wrote many books on the theory of digital audio filters and things like that. Like, he decided to write everything he knew in Faust, and he went on sabbatical, and that was a sabbatical basically, like just writing the Faust libraries. And so so now this is all open source. People can use that. It's really state of the art, you know, and that's why Faust became quite popular because it's a very good way to generate C++ libraries for audio signal processing, basically. And yeah. So for the demo that I'm about to give you now, we're going to use an online tool. You can use Faust directly in the web. Feel free to actually try it now, and it's called the Faust IDE, and you have the URL right here. So, so I'm going to go to my web browser. And so as you saw, I had some issues getting audio out of my computer. First, we blamed it on Linux, but then it turned out that the HDMI cable was just disconnected from the USB connector. So, so it wasn't so bad. Anyway, so this is the Faust IDE. So you can write code in the Faust IDE, and you can visualize what you write in real time. So Faust is a data flow language. So everything that you write can be represented as a block diagram. So here I have a Faust program which just outputs 1, okay? And so, so if I try to actually play it to make some sound, well, it doesn't really make sound because 1 doesn't make any sound. It's a static signal. It's what we call just a DC offset. Well, you hear it when I started, though, because we're pushing the membrane of the speakers forward. And whenever I kill the program, the membrane of the speaker is going back to where it was before, okay? So because you guys are functional programming experts, I'm going to go very, very, very quick in this demo, much quicker than what I normally do. So I'm gonna start right away trying to make what we would call a counter. So we're going to try to increment values here. So the tilde operator, which is here, I don't know if you can see it well, but it's a tilde, okay? So the tilde operator allows me to basically create recursive systems. And so if I write this, then I'm going to create a feedback loop, okay? So I'm basically creating a system where this part here is the feedback, okay? And this part here is the feed-forward portion of my algorithm. So here I create a system where I count 1 by 1, okay? So I basically add 1 every time to the loop. So here I have a loop as a block diagram. So I'm not going to play that because it's not going to make any sound, but just to show you that I'm not lying to you, if I plot the output of the program, you can see that I just have a ramp going from 0 to the infinity, basically, okay? Cool, so After that, what I'm going to do is that instead of now adding one by one, I'm going to try to add a small number every time, so that I basically do increments. I do the increments a little bit slower. And to do this, I'm going to create a function. Okay, and this function is going to be an oscillator function, okay? Because the goal of what I'm doing here is we're building an oscillator from scratch. We want to make sound, so we need to create an oscillator, okay? So basically, I'm just going to take this here. Now I have a function, and this function is my oscillator function, which I'm calling just here, okay? And so now the program is still valid, okay? So in Faust, you can create local variables. So to do this, you can use the with environment. So everything that goes between these curly brackets here will be local to the function that I'm declaring here. And so here, what I want to do is that I want to create a period in function of a frequency, okay? So here I'm creating an f parameter for the function that I'm writing here, and the f parameter is basically going to be, for example, 440, okay, because I want to create, again, an oscillator. So here we just want to have an A, okay? And so what I'm going to do is that I'm going to say that f here is going to be divided by the sampling rate of the system, okay? So in Faust, I can retrieve the sampling rates, so basically the number of samples that are processed by the system at a given moment in time, okay? And so here I'm creating a period in function of that, okay? So now instead of adding one, I'm gonna add the period, okay? And so now if I plot the values, you can see that the values now are ramping up much slower than before, okay? So if I want to create an oscillator, I need to reset this every periods, basically, okay? And so to do that, I'm gonna add something to my loop, okay? Which is basically just going to take the fractional part of the numbers that are going through my loops, and to do that, I'm going to connect, so colon is the connection operator in Faust. Okay, so here I'm adding P to the signal. Now I'm connecting this operation to a function which is going to just give the fractional part of a number. So if your number is, say, 1.1, you will get 0.1, okay? And now if I plot the values, oh, look at this, now I have a sawtooth wave, okay? So in theory, if I were to play this now I get sound. It's not a very beautiful sound, so we're gonna try to make it slightly more beautiful, and to make it slightly more beautiful, we're gonna try to turn it into a sine wave. And so for those of you who already made sound with a computer, like the hello world of sound on computers is actually making a sine wave. So how am I gonna make a sine wave out of this? Well, I'm just gonna say that I'm gonna take this whole operation here, okay? And so I'm gonna connect it to another operation. That other operation is just going to multiply this by 2 multiplied by pi, okay? You probably see where this is going, okay? So now I'm outputting numbers between 0 and 2 pi, okay? And so now if I just connect this to a sine function, the sine mathematical function, so now I should get a sine wave. Okay, very cool. So you see that as I write the code, the block diagram of the system that I'm writing is being updated and outputted here. Okay, now it's very legible actually. You know, like you see that we have our loop where we add p every time, where we take the decimal part of the numbers. That's like a modulo operation, sort of, right? In this context. Then we multiply everything by 2 pi, and then we send that into a sine wave oscillator. Okay, and then you can click on those to see what happens in there. Okay, so the block diagram is interactive. Cool. So I have an oscillator, that's nice, but I would like now to control it. Currently, I cannot really control it. Well, I could do sort of live coding per se, like so for example, if I wanted to change the frequency in real time, here you see that it's being updated on the fly. For those of you who are curious about how this happens, so the Faust compiler is embedded in the web page here. It was compiled with Emscripten, okay? And the code generated by the Faust compiler here is WebAssembly. The WebAssembly code generated by the Faust compiler is put into a node of the Web Audio API, which runs in the web page. So everything you see here happens locally. There is no server involved right now, okay? Cool. So the next step for this demo is that I'm going to create a user interface. Okay. So for this user interface, I'm going to add a slider so that I can control the frequency. And I'm going to call the slider freak. Okay. So this is a variable, which could also be a function, or depends on how you look at it. Okay. And I have user interface elements that are built in Faust as primitives, okay? And so here I'm going to create a primitive that I'm going to call frequency, okay? And so I have frequency. I'm going to say that by default, the value of the slider is going to be 440 hertz. The minimum value is going to be 50. The maximum value is going to be 2000. And the step of the slider, so the precision of the slider is going to be 0.01, okay? And then if I plug freak to oscillator in here, and if I run the program again, okay, now I can actually control the frequency in real time. So that's pretty cool. Okay, so another thing that I'm going to do just to complete this demo here is that now I want to control the gain of the slider, so the volume of the sound that I'm producing. And so to do this, I'm going to create a gain variable, okay, and this gain variable is going to be controlled by another slider whose name is going to be gain. The default value is going to be 1, the minimum value is going to be 0, the maximum value is going to be 1, and the step is going to be 0.01 as well. Okay, and then I'm going to be able to multiply this by gain. There we go. So now I have a way to control the volume of the sound that I'm producing. Okay. Cool. So far so good. Is everyone okay? Yeah. Good. Perfect. So now I would like to try to turn this into something a little bit more interesting, because an oscillator is something pretty trivial and pretty basic to do. I'd like you eventually to be able to make sound on your smartphone at the end of the day, you know, and currently this is a little bit too limited. Okay, so usually in sound design, a way to improve the sound that you make is to add reverb. Okay, and that's a very, very common trick. So if you want to make a sound that sounds very dry, very synthetic, if you want to make it sound more natural, you want to add artificial reverberation to the sound that you're producing. Okay, so here, because we're doing everything from scratch, I'm going to create an echo so that whenever I update the value of the things that I'm writing here, I get an echo on the sound that I'm producing. So I'm going to create an echo function, and my echo function is going to be very similar to the oscillator that I just wrote. So it's going to be based on tilde, it's going to have a plus, and then it's going to have a delay. Okay, so in Faust, to create a delay, we use the @ operator. Okay, and then I'm just going to set the value of delay to be a certain number of samples. So for example, 10,000. And then I'm going to multiply everything here by 0.5, which is going to correspond to the feedback of my echo. Okay. So then if I connect my oscillator to my echo, okay, and if I run the program again, now I have something that already sounds a little bit more interesting, but that is a little bit slightly saturated. This is probably because of the speakers here in the room. Okay. Very cool. So, I have my delay here of my echo. I would like to control it in real time as well. So to do this, I'm going to create arguments to my function. And I'm going to create an argument that's going to be basically the duration of the delay in seconds, okay? And another one which is going to be the feedback, okay? I'm going to say that feedback is basically replacing 0.5 here, and dsec is basically just going to be dsec multiplied by the sampling rate, okay? So here we're computing the number of samples that we want for our delay as a number of samples as opposed to a duration in seconds, okay? Then if I give the arguments here and say that, for example, I have a delay of 0.5 seconds and a feedback of 0.5, then if I run the program, it still works. Okay, very cool. Great, so I promised you that we were gonna make an app with this, okay? To make the app, what would be really cool is if we can control these different parameters using the accelerometers of our smartphone. You know, this is what we're going to do here. So in Faust, it's very easy to map accelerometers to parameters of something that you do. So for example, if I want to map the frequency to a certain axis of an accelerometer, I'm going to use squared brackets here in the name of the slider that I'm just creating. And I'm going to use the ACC keyword. And then the ACC keyword is going to allow me to specify the axis of the accelerometer. So 0 here is for X, 1 would be for Y, 2 would be for Z. Okay? And then there is different mappings that I'm not going to talk about here because we don't really have time for it. But if you're curious, this is all available in the Faust documentation. Okay? So now the frequency is going to be controlled by the x-axis of the accelerometer. Actually, I'm probably going to control it with the y-axis. It probably makes more sense in this context. And then gain is going to be controlled by the x-axis. Okay. So to do this, I'm going to do that, okay, and I'm going to add 0. Okay, cool. So how do we go from this to an app that will potentially work on our phone? So here you have a little truck. If you click on the little truck, you're going to be able to export your Faust program to a very broad range of platforms. Okay, so you see there is Android, there's OS 6, there's Windows, there's many platforms that are supported. So those are the architectures that I was telling you about earlier. Okay, and I'm going to give a name to the app, and I'm going to call it like Lambda, of course. Okay, so the name of the app is going to be lambda.dsp. And then what I'm going to do is that I'm going to export this as a web program using an architecture called PWA. So PWA is basically a web app that you can install on your smartphone. Okay. If I click on compile, then if everything goes well, I'm going to get a QR code. And you guys are all invited to scan the QR code to see what's going to happen with it. So here I'm going to take my phone, okay, scanning the QR code, and then if you click on the QR code, my phone says that it doesn't have access to the internet right now, but we should hopefully hear some sound in the room. And I've never really tried the server with so many people trying to download the app. so let's see what happens. I hear it. That's good. So you guys are in a better shape than me right now because for some reasons I lost the internet connection on my phone. Well, that's nice because everyone seems to be working on some phones, so that's good. So if you want to install the app on your phone, because when you open this, it's a web page, right? If you click on the button, which is on the top right corner of the web app, and you choose the option that says desktop site, then you will be able to actually install the web page on your phone, just like if it was an app. Okay, so I still don't have internet connection for some reasons. This is crazy, of course. Yeah, like this never works when it has to work. You know, like I was having this conversation with someone just before that, but I really like to have the app though. Okay, now it's actually working. Okay, well, worked for you. Anyway, so this is kind of the idea. So basically, it's very easy to go from a Faust program to pretty much whatever you want, you know. And so Faust comes with a very broad range of libraries that can be used for many different applications, you know. And so if you're curious about knowing more about the language itself, you can visit the Faust website, which is faust.gram.fr. Okay, cool. So I'm sure many of you might have some questions at this point, but I will take questions at the end of the presentation, and so I'm going to save time for this later. Okay, cool. So I'm going to get back to my slides to show you the kind of research that we do now around Faust and embedded audio signal processing. Okay, so because some of you might not be completely familiar with this, so I just wanted to give you an overview of what embedded real-time audio DSP is. Okay, so embedded real-time audio DSP is something that you find absolutely everywhere in this room, in your daily life. You know, like you have embedded audio DSP on your phone, as we just did with the smartphone app. You have it in your noise-canceling headphones. You have it in your digital synthesizers, in your digital mixer, in your very fancy car. If you have noise-canceling speakers in your car, in your very fancy sound system in your living room. So it's basically absolutely everywhere. So traditionally, to do embedded real-time audio signal processing, people have been using the processors that are listed here. So they range from microcontrollers to digital signal processors, FPGAs quite a lot, ASICs for very specific applications, and also CPUs, GPUs, etc. Okay. So there are a lot of challenges which are related to doing embedded real-time audio DSP. So the first one is that the real-time constraints are very high. And this is something that you don't necessarily have for other kind of fields. In audio, you have to process, say, 48,000 samples in 1 second. If you miss one sample, you will hear it, okay? So it means that you cannot really use virtual machines, you cannot really use interpreted languages or things like this, because it's gonna be too heavy. So it means that in general for audio, Python or JavaScript or, you know, like any language that's basically interpreted, it's just not gonna work, you know, like so usually people who do audio, they will use C or C++, you know, or like languages that are compiled languages, well, that compile to binary at least, okay. So audio latency is a very important thing in real-time audio DSP, so usually you want your system to be very reactive. If you're a musician, if you're going to use a keyboard like this, if it takes more than 10 milliseconds between the moment you're going to press the key and the moment you're going to hear the sound, then it's going to be a problem, okay? So usually the round-trip latency latency, so the time it takes for an action to come in, so for example, a sound to be taken by the system, and for the sound to come out, it's probably going to take about 10 milliseconds, okay? So at the very least. But there are some applications that require a latency the which is even lower than this, okay? And then ease of programming is definitely an issue because, again, Python, JavaScript, like the bad languages that people use normally for doing like basic programming are not really an option. And in some cases, you have to use things like hardware description languages if you want to program FPGAs, for example. Okay, and you have limited resources, which is a trait of embedded systems in general. So Faust very early on started targeting embedded systems for real-time audio applications. So there is a non-exhaustive list of the different platforms that Faust has been supporting for this. But if you're interested, on the Faust website, there is an exhaustive list of all the platforms and projects that are based on Faust for doing embedded audio. And here we have iPad applications, we have guitar pedal effects, we have analog, virtual analog synthesizer modules. For those of you who know what those are, you have FPGAs, you know, like, so there is a very broad range of platforms that are supported by Faust. And this is kind of a list of the kind of microcontrollers and DSPs and FPGAs which are currently supported by Faust for embedded audio applications. Okay, so one thing that we really focus on in the team in which I am at INRIA is embedded immersive audio applications. So I'm really going through a lot of different topics during this presentation, but you know, I felt like this was the last presentation, so you needed to see something a little bit different, right? So what is immersive audio? So immersive audio is basically like doing home cinema, but with a lot of speakers. You know, like in your living room, normally you have like 5 speakers, you know, if you're crazy and if your wife or husband actually lets you do it, because it requires a lot of wires and a lot of stuff to be installed everywhere, right? So what we do with immersive audio is that we're not happy with only 5 speakers. We want to have a lot of speakers. When I say a lot, it's going to be like 20, 40, sometimes 100, sometimes 1,000, you know, and there are systems like that in the world that use a tremendous amount of speakers. Okay, so for example, here you have a view of the ambisonics system. Ambisonics is one of the techniques that is used for immersive audio, and that's a system at IRCAM in Paris, but most places in the world, like most cities in the world, have immersive audio systems like that. Okay. So one thing that we're interested in my team is to be able to create immersive audio systems like the one you see here, but using thousands of speakers. And there is a need for that. I'm going to give you an example. There is a venue in Las Vegas. Maybe some of you heard of it. It's called The Sphere. The Sphere in Las Vegas has 167,000 speakers in it. And they all need different audio channels. So you need a tremendous amount of computation to actually manage a system like that. And so one of the things that we're looking at in our team is to be able to synchronize a bunch of small, tiny microcontrollers so that the computation of the sound of all those speakers is distributed. And so this entire system here is programmable with Faust. So you write code in Faust, and then the parallelization of computing is done automatically throughout the network. And we make sure that each speaker produces sound in a perfectly synchronous way, right? So this is the kind of things that we do with this kind of systems. So another thing that we've been doing is FPGA-based spatial audio programmable in Faust. Okay, so one thing that you have to know about FPGAs, I'm not going to go too much into the details of FPGAs because again, there was a very nice presentation about FPGAs earlier yesterday, and so FPGAs can manage a very large number of audio streams in parallel because they're very good at computing things in parallel. Okay. So another thing about FPGAs is that they can be interfaced to a very large number of audio chips in parallel. Okay, so they're good at computing things in parallel, and they're good at being interfaced to the rest of the world. Another cool thing about FPGAs is that they can achieve very low latency because they're kind of close to analog in many respects, right? So they don't have the same problem as a laptop, they don't have the same problems as a smartphone or any system like this. They don't have an OS or things like that. So it means that you can really achieve very low latency with them. And thanks to the work that we've been doing for the past 5 years, you can now program FPGAs from the AMD Xilinx brand using Faust. That was a lot of work. I'm not going to go into the details of this, but basically you can now program FPGAs at a high level using Faust for real-time audio applications. Faust already has a bunch of libraries for immersive audio, so like wave field synthesis, ambisonics, VBAP, all the techniques that I talked about before. So it means that, in theory, you can create a spatial audio system based on an FPGA that's entirely programmable in Faust, and that's potentially very accessible. So in order to do this, we started making all sorts of PCB boards. Like we're a hardware team, so we can do things like that. And so we started making boards like this. So this one gives you 32 audio outputs, where you can just connect speakers directly to them because they're amplified. And if you stack them, you can get up to 256 audio channels out of the system. And so then we started building things like this, which are programmable in Faust. And so this thing is a sound bar based on 32 speakers, and it basically allows you to produce sound that are going to sound like they're from behind the bar or from above the bar. So you can create like crazy sound specialization effects using this kind of systems, using code written in Faust, and using the FPGA, which is basically the only platform that will allow you to do things like this the way we're doing it. Okay. Then we try to do the same thing with immersive sound systems, where you just put your head in it. And so this one is a student project. It looks like a student project, right? And it's very wacky, but it works, And it costs around 700 euros to make. And for 700 euros, you can have a system that actually puts you in a completely immersive environment, which is something that would normally cost a lot of money if you were not to use this kind of tools. Okay. So more seriously, the reason why we've been doing all this work is to be able to control the acoustics of a room in real time. And so to do that, we put a lot of speakers in a room, a lot of microphones, and we basically do the same thing that what we do with noise cancelling headphones, but at the scale of a room, right? To do that, you need very, very low latency. You need a lot of speakers, a lot of microphones, and so we built these kind of audio interfaces that basically provide a very low latency of 10 microseconds, which is very low for audio applications, and that are completely programmable in Faust, and where you can target up to 512 inputs and outputs. Right. So just to give you an overview of the research project that we had around using Faust for embedded real-time audio applications, which are a little bit like very concrete, basically. Right. Okay, so what is coming next in this world? Well, we want to continue to improve Faust, of course. Faust still has some issues, still some defaults, and so one thing that I want to say, is that people who are in audio DSP are very, very, very much used to using imperative programming languages. I'm sorry to say that here, but this is really something that we're facing all the time. Why? Because people who do this, they are more like mathematicians, and mathematicians are not necessarily computer scientists, and so they know how to use MATLAB, they know how to use R, they know how to use Octave, Python, but whenever like you have to convince them to use a language for the sake of using a language, then things are a little bit more complicated. So one thing that we've seen in general is that it's very easy to teach Faust to kids because they're not biased in terms of how they're going to write code. If you try to teach Faust to someone who's been writing code in MATLAB his entire life, then it's just not going to work well. And it's going to require a lot of convincing. So we're trying to solve these issues, like by making Faust a bit more accessible and a bit more attractive to people in the scientific community who need to do real-time audio DSP and who are used to MATLAB or Python or these kind of environments. So where is this going? So we still want to improve the performances of the Faust compiler, which can definitely still be improved. We want to continue improving supports for complex embedded platforms because there is a lot of demand for this, especially from the industry. And we want to make crazy systems like this. So this is an AI-generated image, of course, but we basically want to create sound systems involving hundreds of speakers based on an FPGA and using Faust for VR 3D audio rendering. We have a project that's just starting on this topic, and so we're really excited. Really excited about that. Okay, I see I have probably 5 minutes left. So just in case I had a little bit more time, I actually saved you a bonus slide for another project that we're doing in this context, which is actually applying everything that I just told you about to cave environments. So it's a very, very concrete application of what we're doing with this kind of technology. So I don't know if you know about this, but in France, in the south of France, there's this place called the Chauvet Cave, and it's a cave that hosts some of the oldest paintings of humanity. It's from 38,000 years ago, so it's very, 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 very old. It's not open to the public, and only scientists can go in there, and they really believe that there is a correlation between the places where the paintings were done and the acoustics of the place, because I know people probably found it like cool, at the time when they were doing those paintings. Caves were basically the only places in the world where you could actually experience acoustics, right? And so there was probably a correlation between those different things. So the cave is beautiful. The paintings are absolutely incredible. Like, come on, this is 38,000 years old, it doesn't look like it's 38,000 years old. And I'm just gonna move quickly. So in order for people to actually visit the space, there is a replica of the cave that you can visit that's right next to it. And the replica is basically just made out of painted fiberglass, right? It's a lot of tourists go there in the summer. There's air conditioning too. Like Ardèche is very warm in the summer, so it's also like a good way to escape the heat at some point. And so we are in the process of collaborating with them to actually add virtual acoustics to the replica of the cave. So to do this, we will use all the technologies that I just told you about in this presentation. So functional programming, FPGAs, and real-time audio DSP. Anyway, I hope that I didn't lose you too much with this presentation that was very dense and probably a little bit different from what you're used to. But if you have any questions, I will take them now. And the slides are available at this address if you want to check them out later. Well, thank you very much.
Thank you. That was amazing. Are there questions? So people should come down and use the mic at the front, I guess. Oh, and there's a mic in the middle as well.
like very practical thing. I looked at a few libraries, different languages, and I found it's just probably super hard to learn to think in oscillators and nodes, and you kind of have to spend like a few years building this brain map to actually work with those. So I wonder, is this like, I think people could be like seduced thinking, oh, I'll just come back home and like over the weekend I'll come up with something, and then no, it's super hard, I think.
Yeah. So that.
And just another thing is like,
Yeah.
I wonder how likely is that would be that LLMs would be able to kind of synthesize something meaningful when you ask them, and they will reuse this language and build some kind of a code that's.
Yeah. No, I think that's a, well, thank you for the question. It's a very good question, very smart question, actually. I'd say there are two kinds of people who use, well, Faust, or people use Faust in two different ways. I haven't talked, so here in my demo, we built more or less everything from scratch. And the point was so that you see like the semantic of the language, you know, and kind of how it works. But as I said, Faust comes with libraries. And I would say that definitely more than half of the people who use Faust don't write things like this. And basically will just use objects that are already implemented in libraries and just connect them to each other, you know. And so in a way, that's why I think Faust is reasonably accessible to a lot of people, because even if you don't know how to understand something like this, you'll always be able to use something that's already written in the libraries, and the libraries are very, very diverse. So there is a lot of things in the libraries. Now, as you said, to answer maybe your second question, so sound design is a skill that takes a lot of time to build. And it's very much connected, especially if you do things from scratch, just like we did it here. It's very much connected to signal processing. And so I think it's really hard to imagine that someone is just like, you know, in just a few weeks is going to be able to make like completely new sounds or completely new systems starting from scratch. I mean, it's probably impossible. Like, I mean, it takes people like years to get these kinds of skills. On the other hand, you know, like a thing that a lot of people do again, you know, is as you would do with modular synthesizers, you take existing blocks, you connect them to each other, and then you can experiment with that, you know. And I think that most people who are musicians and who don't have the skills that I just talked about, that's what they do when they try to use Faust. I hope that answered your question. So, okay.
You mentioned you're using Faust on all of these systems with a whole bunch of speakers all connected together. Is like the issues of getting the signal in time to all these speakers and keeping them synchronized, is that something that you're able to handle within Faust, or do you need external functionality for that?
Yeah, good question. So Faust originally was thought only for audio processing. So the control layer is missing in Faust, sort of. Yeah, I mean, you could do some of it in Faust, but usually when people want to make something where there is a lot of control, they will use a different environment. So if you are like someone from the like music technology or computer music community, you're probably going to use like MaxMSP or Super Collider or you know, like these tools. If some of you know about them, you know, and those are very or Chuck. And so these tools are very good for the control layer, and so you will use Faust to take care of the DSP portion of your program. Then the control layer will be done in a different environment, you know. And like one thing that works very well too, you know, is to build physical interfaces which will just output MIDI, for example, control messages, and then control a Faust program using a physical interface. But yeah, no, Faust is not really made to make music. It's made to make sound, basically. So yeah.
Hi, great talk, thanks. I'm just wondering, so the language itself, I'm having some problems characterizing it. So it's somewhat a language to connect bits, or is it functional, or is it both? Can you maybe say some words about that?
So I think Faust is very functional for sure, and Faust originally is really thought of as a language to make block diagrams, right? So, the main idea of Faust is that you have to connect something to something, and it's a data flow language. So, when I started the demo, started just with one. So this is a generator. This is a block that's generating signal, and it's just generating a stream of ones. There is no types in Faust. Everything is a signal. Under the hood, types are inferred from the program that you write, and this is done automatically. But because you're only considering audio with Faust, it's a domain-specific language. Everything that you do in Faust is manipulating signals. So this is a signal generator, and multiply is basically going to be a function, right? So multiply is a function that has two arguments. And so, for example, if you want to multiply 1 to, 2 to 3, for example, then you can put 2 and 3 in parallel because they are two block generators, 2 and 3, that are outputting signals, 2 and 3. And then if you connect that to a multiply function, then you get a number which is going to be 6. So Faust is functional for sure, at least the way I understand it. Maybe some people here will disagree with that. I know it's a sensitive topic. I talked to many people throughout the past 2 days where there seems to be different definitions of what functional really means. But I think it's functional for sure, and it really targets building block diagrams, basically, because that's what you do when you do signal processing. So, yeah.
Okay. Thank you very much.
Sure.
Do we have time for one more? One last question.
So you mentioned that Faust doesn't really concern itself with the control layer.
Yeah.
But I see it compiles to WebAssembly. So would you consider it feasible to kind of do the control aspect in JavaScript?
Yeah, of
or
course.
any other language that compiles to JavaScript? And in which case, is there any other, is there any such a project?
Yeah, I mean, if you click on the export, the little truck, if you choose web, and if instead of using PWA, you use WASM.js, so this is WebAssembly and JavaScript, then it will generate a web page, standalone web page where you have a control interface which is very basic. It's just like sliders, and it shows you how the sliders can control what's happening in WebAssembly on the other side. So there are a lot of people who do that actually. If you want to do real-time audio DSP on a web page, then Faust is very good because you can just generate a block which is going to be WebAssembly, and then you can plug whatever you want on top of that, HTML or JavaScript or whatever, and it will work, and it's pretty straightforward. There is a very clean API to do this, so yeah.
Okay, so potentially you could see kind of some live coding
yeah, of course, yeah.
kind of running on the browser, doing using Faust for the synthesizing.
Yeah, I mean here you can do some forms of live coding, but because Faust still needs to be compiled, depending on the size of the program that you're writing, compilation might take half a second or a quarter second or something like this, so it takes some time for the program to be rebuilt, but if you use objects that are already like pre-implemented, then you could do like real live coding, and there are live coding environments that are actually based on Faust, so yeah, sure, thank you.
Okay, thank you very much.
Thank you.